Hey guys, just wanted to clarify some things from today's class and extend what we learned about arithmetic and geometric sum equations. One of the bigger side topics that we have to deal with is dealing with subscripts and how many terms or what term we're dealing with. And I think a lot of people get confused with this once we start throwing formulas of maybe how many numbers we're adding up, which one's the last one, which one's the first one. So I just want to look at the idea of a sub 15, what that means. Now we talked a lot about subscripts might be time or what step you're at, but that really depends or is determined by where your sequence starts also. For example, if my actual sequence starts at sub 0, what's hard to understand is that a sub 15 is the 16th term in the sequence because I count a sub 0. If you're counting on your hands, we don't always count 0, but now we have to say that that is a term in the sequence, so it needs to be counted. We do have sequences that start other places, like at a sub 1. If it started at a sub 1, that would be the counting numbers. When I say 1, 2, 3, that's what my fingers are doing. But when I start at 0, I'd put up a finger and say 1. Or sorry, I'd say 0. So if it started at a sub 2, for example, it would be the 14th term of the sequence. If it started at a sub 14, this would be the second term of the sequence. So a big thing that we do with these sequences with like geometrics, arithmetics, we always try and find that function formula. And a big thing to think about that when we're talking about a sub 15s is functions start at 0. That's a really big thing to notice that they have or start at a sub 0. So how we find specific terms, if I want to find the 15th term and the 16th term, might be confusing in the next couple steps. Something we talked about also is how many terms there are. We have in our sum equations, sum up the first 50. Well, then you know there's 50 terms. But if I say I want the sum from a sub 12 to a sub 39, I have to know how many terms. Now, you can count in your hands, maybe some smaller examples, but to generalize it, what you're going to have to do is take the large subscript minus the small, and then add 1. So like from 0 to 9, there are 10 total terms, which again, that's probably the easiest example to count on your hands. That when you say 0, you're actually putting your finger up. So we count the first and last terms. Both are in our sequence. Now, one of the things that we'll have to do is make equations or functions from different sequences. And I just want to show you a quick example. If you have a tough time making a linear equation or knowing how many terms there are, it's called adjusting the linear, or I call it adjusting the linear. Let's say we have a d, some common difference that equals 4. So I know the sequence is going up by 4 each time. And let's say the sequence, I don't know exactly where it starts, but a sub 5 is 10, and a sub 58 is all the way up at 222. So what you can do to write the linear for this, let's say I want to find a sub 76. Well, I could add 4 a whole bunch of times and I'd probably get lost. I know the function starts at 0, so there's two things you could do. You could work backwards and subtract 4 a whole bunch of times to get to a sub 0, which might do a little work, but there's another way by adjusting your linear. And here's what it would look like, is that my sequence, I know the d is 4, but let's just say I kind of make up the y-intercept of 10. What I can do is adjust my n values to shift this whole sequence back 5. Now I want to shift it back 5 so that this 10 lands on a sub 0. So that's what I would do with n. Now if this was a sub 0, it would be 4n plus 10. Easy enough. But since I can shift it and move it back to a sub 0, I have this 4n minus 5. So if this was a sub 13, I'd have n minus 13. If it was a sub 20, I'd shift it back 20. Now notice if I solve this, you distribute the 4, I get 4n minus 10 or minus 20 plus 10, and the sequence would be 4n minus 10 starting at 0. You can see if I subtract 4 enough, 4 times 5 will subtract 20 from that and adjust it back there. So if I want to find a sub 58, I can plug in 58 into this equation and then eventually find that 222. All right, so that's just talking about how to find specific terms, understanding what that subscript is. But then we used or ran into arithmetic sums. So we talked about Gauss a little bit. This is the Gaussian formula for finding the sum. It takes the number of terms times the first term plus the last term, all divided by 2. So I want to look at some problems that we would give you where you're missing some things. So if I look at this first sequence, I want you to find the sum of 1, 3, 5, 7, 9 essentially, but we'll have some more gaps in here. So we have to think about what we're missing. It looks like we have the first term, looks like we have the last term, but we don't have the number of terms. So to do that, to find the number of terms in an arithmetic, kind of a step-by-step process here, is find the linear equation. You got to get the linear equation, and that's just finding the difference between successive steps. That's your slope. And then your first number, force it to be your y-intercept. I don't care where the sequence starts, force it to be your y-intercept. So I have this equation y equals 2x plus 1. So what I'm looking for the number of terms is how many steps it takes me to get to 9. So I plug in 9 here for y, and well, 9 would equal 2x plus 1. Solve this for x, and x equals 4. And this is where students get a little, wary and a little confused. X is not the number of terms. What's tough about this is x tells you how many steps you go past the first term. The first term is already counted. It's right here. See that plus 1? That's your y-intercept. That's where the sequence starts. That counts now. That counts in the number of terms that we're adding up. So here's one term plus 4 more terms after that. That's what the x represents. So there are 5 total terms. So if I put that in my sum equation here, arithmetic sum equation, I take n, which is number of terms, which is 5. Now, it may not be a sub 1, it might be a sub 0, it may be just a sub whatever the first number is, which in this sequence was 1, plus 9, all divided by 2, so the sum is 25. And you could check if you added 1, 3, 5, 7, 9, and made it small enough so that you can kind of trust that it works for that. So if we make it bigger, follow the same process. And if you want to maybe stop the video and try this one, might be a good idea. I'll go through it in a second. So the difference between successive steps here is 18. So I can make a linear. The linear would be y equals, 16. 16x plus 4. So I plug in my 116 to see how many steps I went. 116 equals 16x plus 4. Subtract the 4 to the other side, divide by 16. It looks like x equals 7. But that's how many steps there are past the first term, which in this case is 4. That's a very important 4, that y-intercept. That counts. 7 more numbers, 8 total numbers. 4 plus 16 is first and last, divided by 2, it's 480. So that's what you have to do. And it might get a little more complicated to say, well, okay, maybe this is a sub 6, and maybe this is a sub 42. We'll have the spacing for that, but you can still do that same process. So that's how to find an arithmetic sum when you're missing the number of terms. Another situation now is I give you something like this. 5, 10, 15, obviously 20, 25, so on and so forth for the first 15 terms. So now what we're missing is the last term. I need to find what the 15th term is. Now again, I have to find the linear. The linear for this is y equals 5x plus 5. The slope is 5, it changes by 5, and this 5 is where it starts. Here's what I want you to think before I move on, is what would I plug into x to find the 15th term? My hint is this is the first number. The 5 is the first value, and I got to get the 15th number. You should plug in 14 to get the 15th number. Another way of thinking about this, 5 is a sub 0. And what's tough about this, if I'm finding the 15th number in the sequence, that would be a sub 14. Common phrase I use is plug in subscripts when you're trying to find a certain subscript. I got to plug in 14 into the equation to find a sub 14. But this, remember, is the 15th term in the sequence. I made a function so it has to start at 0. This is the 15th term, okay? But eventually that gets me the last value of y equals 75. 15 total terms. Don't mess with that n. We want the first 15 terms. I don't care where it starts, 15 numbers after that. 5 plus 75 divided by 2. Now here's where it might get a little more complicated. Maybe I say a sub 15 is 9, and I want you to add up the first 66 terms. Well, I still need to find that 66th term. Now this can be a little complicated in the way we said before, but watch, I'm going to show you two different ways. Let's look over on the left here. As you can see on the left, I use that adjusting the linear idea. I know the slope is still 2. It's shifted off 15 from that, so n minus 15, and I'll say the y-intercept is 9 for the shifted one. I go through that, and I get an equation, or a linear equation, y equals 2n minus 21. Where the negative 21, that would be a sub 0. Now here's what's tough about this, or doing it this way. I have to find the 66 terms, but that's past a sub 15. So really what I'm finding is a sub 81. 15 plus 66, that's 81 terms. So I got to find the 81st term, just like above. If I have to find the 15th term here, I got to plug in 14. If I have to find the 81st term, I plug in 80. So that might be a little hard to adjust. You're adjusting the sequence back and then jumping back over the top to get to the 66 terms. Here's what I would do, probably a little bit easier. Call this your 0. Think of it as your 0. I'm starting at 9, I'm going up by 2. If I have to find the 66th term past where I started, which was at 9, I just plug in 65. Kind of like the one we did above. I still get 139 from both, but the n is 66. 9 plus 139 divided by 2 is 4884. All right, so that is arithmetic sums, or how to find arithmetic sums. We'll practice a lot more. I think you should be fine with those in the homework. Just be careful of where the sequences start and how many terms they want you to add up. Next, we're going to talk about geometric sums. This one we didn't hit today. So geometric sums, obviously we're dealing with geometric recursives, geometric sequences. Here's a situation that the population of sick people triples every day. Oh no, so we go from 1, now there's 3 people sick, now there's 9 people, 27, 81, so on and so forth. But for a sum equation or a sum idea, the question might be the number of new sick people triples every day, which means we need the total of sick people after that amount of time. The geometric sum equation is as follows. The sum is a sub first. The initial value goes out first. And then inside these parentheses is r to the n, all minus 1, all over r minus 1. So that r, again, is that common ratio. It's what you multiply by each step to get to the next term. N is still the number of terms, the number of terms that you're adding up. Usually geometrics are a little bit easier because you don't have to find later terms. But here's a situation or example of that. Let's find the sum of the geometric sequence of 1, negative 3, 9, negative 27, 81, negative 243. So I start off with it's a little hitch, a little wrench, but you got to find the r, but you just got to think, what do I multiply to get from 1 to negative 3? Well, that's actually negative 3. Does it work to multiply negative 3 by negative 3 to get to negative 9? Yeah. So actually my r is negative 3. And you can have r's that are negative. That's fine. They just kind of flop back and forth. So I plug those into my equation. This 1 is because of the initial value. My r is negative 3. What may be very, 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 very smart is to put that in parentheses in your calculator. To the 7th, so I said the sum for the first 7 terms. We don't have to deal with subscripts or anything like that in this one. We subtract 1, which feels weird, but you get this big whole honking number, and you just subtract 1, and then divide by negative 3 over negative 1, or negative 3 minus 1. And from there, that sum is 547. If it was a positive 3, these would both be positive 3. So you just got to find your r, find the number of terms. Here's an example of where this might be found. You have an ice cream store that sold 22,000 ice cream cones in 2008. It looks like the manager predicts the number of ice cream cones sold each year will increase by 5%. So this is a geometric sequence. And why I bring this one up, is how we ask the questions. Number 1 says, how many ice cream cones will you sell in 8 years? So that's asking 8 years from now, how many cones are going to sell that year. So what I can do is I can make the exponential equation for this. There's my initial value. I have my r to the n. And really all I have to do to find the 8th year is plug in 8. I want to go 8 total years. I'm going to sell 32,504 cones. Okay. The second type of question we're probably going to ask you then is how many ice cream cones we sell total, and we might even say 8 years. Now I changed it to 10 years, but total. Notice that the only word different in here is total. Total is sum. We don't want to know how many you're going to sell in year 10. We want to know how many you sold total in all those years, year 1, 2, 3, 4, and 5. So that's a sum equation. But that would look like this. You got 22,000. That's my initial value. That's my initial number of ice cream cones. Times 1.05. That's my R to the 10th, 10 years minus 1 all over 1.5 minus 1, which is 23, or sorry, it's got to be more than that. 276,714 cones. So these two examples, just giving that or knowing that sum equation, try your homework as best as possible. I think you'll have a little more of an advantage now. But do your best. We'll take homework questions on that tomorrow. See you tomorrow.